while we're waiting for more people to log on. Okay, so as I was saying before, right, I sent your test back, so you should have gotten it in your email, and then the grades are also posted in WebAssign. So your WebAssign, what is it called? Your overall grade, or wait, I can see it right here. Your total right there, my total. Of course, my total is very low because I don't have any grades, but so your total should be up pretty much up to date. So whatever you're whatever you're seeing there, that's sort of your current grade. I haven't put in the as I mentioned last time, I haven't put in the a class participation grade for the first test. So I've got to work on that, and so I'll get that entered sometime during spring break. So that may slightly affect this total, but not that much. So of course, the big impact on your total is going to be whatever your test score was. So now, when I sent back those tests, since I'm typing in, my responses there on the computer, it's hard to type in many comments. So the comments that I put in there are just very brief. So of course, I may subtract points. That's the chief comment, right? So if I'm subtracting points, that means obviously something is wrong there. Sometimes I will put you need to go to the answer key, which is posted now where the test was posted, and compare your test to the answer key. So that's really important in this case, since I can't write too many corrections onto your test, right? So it's really important for you to go back and look at the different problems and see what you missed and correct those, right? So you don't make those mistakes again, either on a future test or on the final exam, where we may have problems, very similar to problems on test number 1 again, right? So you don't want to make the same mistakes on the final exam. Now, sometimes I will put comments on, something is wrong, or a lot of times I will put question marks. So if I put a lot of question marks, that usually means I have a question about the answer or how you arrived at the answer. I may or may not take off points, though, when there's a question mark. So that just means I thought your answer had some question about it, but maybe not enough to take off points. Now, sometimes I'll put okay next to an answer, and that means that it may not be the optimal answer, but it's an acceptable answer. So so that means you should, compare that answer to the answer key, and you got points for it, but maybe the answer on the answer key would be considered a little bit better answer, or you did the problem a little bit in a way that I wasn't expecting, and it was okay, but that's not the way I was expecting the question to be answered. Now, on some of you, not a lot, but in some places, I had to count off for not showing work. So again, I stressed that. And so there weren't a lot of points taken off for not showing work, but I did that sometimes, right? So if I put no work and then counted off points, that means even if the answer was correct, I was expecting to see some work there, and I didn't see any work. So I wasn't going to give you credit, right? So that didn't happen a lot, but that happens sometimes. So again, be aware you need to show enough work to justify your answer, okay? Maybe not as much as I show on the answer key, but some work, right, to justify your answer. That's going to be especially important on test number 2, okay? So you really got to pay attention to that on test number 2, where in many cases we're finding formulas for derivative functions. And so you'll write down the answer will just be a formula for a derivative function. But if you don't show me the steps of how you arrived at that derivative function, if you just write down what the answer is, then you're probably going to lose points for that. Okay, so when you're doing your homework, so while I'm thinking of that, when you're doing your homework for starting with this homework, basic differentiation rules, And then this homework product and quotient rules. These are where we're using rules for finding formulas for derivatives. Well, this one too, chain rule. These are all rules for finding derivative formulas for derivative functions, shortcut formulas, right, for derivative functions, so we don't have to go through this lengthy limit process. So they're very useful rules, but they will require steps, and so get into the habit of, when you're doing your homework, of writing down the steps on a on a piece of paper when you're doing your homework. Of course, you should be doing that anyway, right? Otherwise, I don't see how you're going to arrive at the answer. But get in the habit of writing down your steps, so that when it comes test time, you'll be used to doing that. All right. Now, look, let me warn you, you can find programs, websites, you can find calculators that will compute for you derivative functions. So they will apply these rules and do the algebra for you and compute derivative functions, and you can get the answers, right? So you do not want to rely on such websites or on a calculator that will do that for you. Okay, so be very careful about that, because you're not going to be learning the lessons that you need to learn, and I will catch that on a test. Okay, so you can check your answer maybe using a website or a or a calculator, but don't rely on the website or the calculator to do all the work for you on these homeworks. Okay, or in any situation where we're finding well, there are other situations in the course too, but in particular now, when we're finding derivative functions, I don't think, I found this nifty program and it's going to do the work for me, and this is great, and I'm going to save myself a lot of time. In the long run, that's not going to work. All right, so try to avoid that as much as possible. Right? Okay. Well, actually, entirely, except for maybe checking the answers that you've got. All right. So everyone's sort of clear on that. Okay. So what else did I want to say about the test? Oh, there is one on the answer key. There's one problem. There's one mistake that I made, and I haven't posted the correction. This is problem 6D. Problem 6D, it's finding an average rate of change. And I wrote down the calculation steps right, but I left off a minus sign. There's supposed to be a minus sign on the answer here. There, the answer is something like minus 13.33. You may have a slightly different answer, but it's something close to that. And on the posted answer, I left off the minus sign. So you can be aware of that. Most people got that one right. So at some point I'll fix that, but that's the only one. That's the only thing on the answer key I think is off. Are there any quick questions here about the test? If there's something about the test that you don't want to share with the class, you can ask me after class, or something, or you can email me or something. But is there anything right now that you want to ask me in particular? All right. So, yeah, I forgot the other thing. So, while I'm nagging you and lecturing you here about tests, I said this last time. So, many of you did really well. So your scores were in the 80s and 90s, and that's really good. So, I commend you for your effort there and for your work. If your score was, in the 60s or 70s, 70s is also, okay, right? That's a passing grade. The median score in the class was 72. So that's a pretty typical median for a first test in a calculus class. A median means half the scores were above that and half the scores were below that. So if you were in the 60s or 70s, probably what that indicates is you need to be more careful with the review, right? And so you needed to pay more careful attention to the test review, and you should have visited Madison's review session if you had the chance, or made an appointment with an online tutor in the math center to get help with the review prior to taking the test. So you probably did not prepare for the test properly. All right, is what I'm saying. If you had a score in the 70s or 60s or even below that, right? Probably you didn't prepare for the test right. So you don't want to make that mistake on test number 2, right? So when test number 2 is rolling around, you got to pay more attention to preparing for the test, doing the review, and going to Madison's review session, right? So that trust me, I know this from long experience, that will make a major improvement in your test score. A letter grade or 2 letter grades, okay, is not unusual, right? It's not guaranteed, but it's not unusual. So, so really, you've got to make that effort, right, for test number 2, in addition to continuing doing your homework. Now, some people did well on the test, but their homework scores are not great. So you don't want your homework score to be dragging down your overall letter grade, right? So please be participating in the homework, all right? So you don't want to have a good test score and then have a low homework grade and have that drag down your overall grade, all right? That's really silly to do that. So keep up with the homework, because not only will that give you a good homework score, but that will also, of course, be another way of preparing better for the next test, right? Okay, so want to stress that most of you are doing really well on homework. So there's just a few of you that are maybe not having good homework scores or not turning in homeworks, especially not turning in homeworks or not, when I say turning in, not completing the homeworks right, that you really got to avoid, right? So you really got to be working on your homework. Okay, all right. So there's all my nagging for today, and so I'll stop that before spring break here, and we're going to go do our notes. So again, any questions at this point? All right, so we got a lot of people finally logged on here. So this is going to be kind of an important class because we're going to be talking about, again, differentiation rules. So these are the rules we can use to help us find derivatives, right, without having to go through this lengthy limit process. Oh, speaking of this lengthy limit process, right, that is the nature of the problems in this homework, right? There's not that many, but these are not going to be easy homework problems. This is due on Saturday, okay? This is due on Saturday. I moved it back to Saturday to give you a little bit more time. Notice that then, since we're on spring break next week, other things will be due after spring break. So but you don't want to let yourself get too lazy during spring break. You want to be working on these homework assignments because these are lengthier and they're going to be due quickly after spring break. This one especially will certainly be due on Tuesday after spring break. But this one you want to work on as well because this one is a long assignment. So you need to get as much of that as you possibly can get done by spring break. Are there any questions about this homework assignment, though? I know a lot of you have worked on it, even though it's not due till Saturday. Any questions about that? Any problems on there? So this is executing that limit process to find a derivative function, and we're going to make all that obsolete now rather quickly by learning these rules, right? But we will have problems like this on the test number 2. So you do need to go through the steps in these problems kind of carefully. All right. So if I'm not hearing any questions, I'm going to assume there's not any. But then I don't want, then when I ask this question, test number 2, I don't want to see a bunch of nonsense written down. Okay. I want to see good responses to these sorts of questions, right? These are the questions where, you have to compute the limit as h approaches 0 of, that average rate of change quotient in order to derive a derivative at a particular number or a derivative function. Okay. All right, so we've done that several times in the notes, so you've got that in your notes, examples of that. So you can follow those examples, but it's still something you have to practice. Even if you've seen examples, it's not straightforward until you've practiced it. Okay, let me switch now to the notes then. And last time we were going through our basic differentiation rules. So these are the basic rules we're going to use to find derivative functions. And we learned 4 rules last time, 3 of which are really key. There's a 4th one, which is a little bit more straightforward, but the 3 that are really very important to us are the constant rule, what's called the constant rule, right? Which remembers that says the derivative of a constant, that's the derivative of a number, is 0, always 0. All right, so that's a very important rule. It's easy to remember, but it's important. We use it a lot. Okay, the next one is, and this one is really crucial, is the power rule, right? So that is the rule that we use to find derivatives of expressions that are powers of x, like this one, right? Okay, you use the power rule to find derivatives of things like x cubed, or x to the 4th power, or x squared, or x to any power, actually. All right, it doesn't have to be a whole number power. So that includes negative exponents and fractional exponents as well. So the power rule is really incredibly important in calculus in helping us find derivatives. We're going to probably use that rule more than any other rule. And then the last one is the so-called sum rule. And remember, if you that's useful if you have a function formula which has lots of terms in it. Terms are quantities that are added or subtracted. So like in this function, right, this formula consists of 3 terms, because you've got x cubed added to this second term, 3x squared, and then you have subtracted off this 3rd term, which of course is the -1, right? And the sum rule tells us, well, if we want to find the derivative of a formula like that one, then that's simplified, because we can just find the derivative of each term separately, right? So if I want to find the derivative of x cubed plus 3x squared minus 1, I can do that just by finding the derivative of the x cubed, do that, and then find the derivative of 3x squared separately, do that, and then find the derivative of the -1 separately, do that. Okay, so we can treat differentiating this formula just one term at a time. Okay, and that makes our life much easier, right? Because the terms are much simpler expressions than the entire formula is altogether, right? So that allows us to break down this formula into different parts and find the derivative of the different simpler parts. So those were the 3 important rules that we learned last time. Well, we're going to practice those right now, because we still have some examples that we want to go through. Okay, so let me move myself around here so I can write easier. And so let's do this, right? I want to find the derivative of this formula, x cubed plus 3x squared minus 1. So to indicate that I'm taking the derivative, since I've got this formula written as y equals and not f of x equals, to denote the derivative, I'm going to use the old-fashioned derivative notation, which would be dy over dx, right? But remember, that just means derivative. Okay, so that's what I'm doing here, is finding the derivative. All right, so to find the derivative of this sum of all these terms, I'm going to do each one of the terms individually, right? So first, I'm going to find the derivative of x cubed, and that is a power of x. So that being a power of x, I can apply my power rule. So remember what the power rule says, right? You're going to bring down the 3, right? So easy, and then subtract 1 from the exponent 3. So you'll get left with 3x squared. What could be easier than that? See, the power rule is very easy to use, and it applies in lots of situations, because many times in our formulas, in our function formulas, we're going to have powers of x, And so that's why it's such a useful rule. It's easy to apply, and we get opportunities to apply it frequently. What about the derivative then of the second term, 3x squared? This also is a power of x. The x squared is just a power of x, right? So again, you can bring the 2 down. You don't have to concern yourself with the 3. You're just going to keep that in your derivative formula. That was actually the fourth rule that we learned, that called the constant multiple rule. I didn't mention that one as being one of the important ones, but we're going to use it. But it's so easy to remember anyway. Okay, so I'm going to bring the 2 down right in front, and of course the 3 is going to stay there, and then I'll have x to the 2 minus 1 power. Well, that's x to the first power, or you could just write x. You don't have to write the 1 there. Okay, and finally now, for the third term, we have this as a constant. So this is not really a power of x. If you want to, you can think of it as a power of x, but it's really just a number, right? And so what's the derivative of a constant always? Someone?
0.
0, right. The derivative of a constant is 0. So so Damien, we just end up here with, for the derivative of -1, we just end up with 0. So you have now a nice formula here for your derivative. It's 3x squared plus 2 times 3 is 6, right? So plus 6x, and then that's it. Okay. So there is the derivative of this function. So this is the formula you can use now to find the rate of change, the instantaneous rate of change at any x value that you like. So see that now, that formula now gives you lots of information about the graph of the original function f, the graph of this original function here, right? Okay, because you can use this formula to, again, find the rate of change at any value x, and the rate of change tells you things like where the function is increasing, right, and where the function is decreasing. So by looking at this formula, you can answer questions about the graph of the original function without actually going through the process of making the graph. That's the whole point of, or one of the points of, maybe not the whole point, but that's one of the nice features of derivative functions. So actually, let's use the derivative function to answer a question about the graph of x cubed plus 3x squared minus 1 without actually drawing it. So here's my question. I want to find the values of x where the tangent line is horizontal. So on the graph of this function, which I have no idea what it looks like, okay, I may have a vague idea, but I don't have a really good idea of what it looks like. I want to find where is it on that graph, or what values of x will the tangent line be horizontal? Okay, maybe there's not any, but if there are, I want to find them. So how can we answer that question now without looking at the graph? You know, this is really kind of a geometric question, right? So how can we answer this question algebraically without actually looking at the graph? Do y'all have some suggestions there?
Wouldn't it happen at a turning point?
It would happen at a turning point. That's right. Absolutely, Colin. It's going to happen at a turning point. That's where the tangent line is going to be horizontal. Okay. So what we're really looking for here, Colin, this question is kind of disguised here. This is really a question about where the turning points are, right? Okay. Kind of asking a kind of a roundabout way. So what we're really looking for here is, you're exactly right. It's the turning points. And Colin, at the turning points, right, where the tangent line is horizontal, what is the rate of change at turning points?
0.
0. So, see, that's the clue, right? So what we're looking for is where the rate of change is 0. But so now how can you find where the rate of change is 0 now? By doing what?
Set the equation equal to 0?
Set, yeah, what equal to 0?
The derivative.
Derivative, right? You set the derivative to 0. I can't stress this lesson enough. Okay, we've said it numerous times already, but let me just repeat it. The tangent line is going to be horizontal, or the rate of change is going to be 0. Those mean the same thing. Okay, when the derivative function is 0, right? Because the derivative function is what gives you rates of change. So when you're asked a question like this, where the tangent line is horizontal, that's the same as asking where are there turning points. You're going to look for that where the derivative is 0. Oh, by the way, Colin, now this is interesting. Where the derivative, so here's the derivative function, and we're setting it equal to 0. Colin, normally when you set a function equal to 0, what are you looking for that function? So for the derivative function, don't pay attention to this function for a moment. But for the derivative function, when I set that equal to 0, I'm going to solve that equation. What are you normally looking for when you set a function to 0? You recall?
You mean maybe?
If let's go back to this function. If I set this function to 0, not the derivative, but the original one, if I set that one to 0, I'm not doing that, by the way. Okay, but if I were to set that to 0 and solve this equation, what would I be finding on this function?
Intercepts?
The intercepts, right? Okay. Well, look, to find where the turning points are on this function, let me scratch this out now because this is not what I was doing. All right. But to find that where the turning points are on this original function, you're going to find where the x-intercepts are on the derivative. All right. Okay. So that's an important lesson I want you to keep in mind. All right. To find where the turning points are or where the tangent line is horizontal, you're looking for really the x-intercepts of the derivative. See, we always are in algebra telling students about finding x-intercepts, right? That's so important to find x-intercepts. And I think it's sometimes mysterious to students why it's so useful to find x-intercepts. You know, it's important to know where the where the graph crosses the x-axis, of course, right? But why do we stress it so much? Because that same problem is going to recur, okay? Finding the turning points of a function is really an x-intercept problem all over again, but it's the x-intercept of the derivative, not the x-intercept of the original function. All right, well, okay, so let's solve this equation now. So let's find the x-intercepts of the derivative. This is an easy equation to solve, though, right? You can solve it by factoring. You can factor out 3x, and you'll get left with x plus 2. 3x times x plus 2 equals 0. And so that means either 3x is equal to 0 or x plus 2 is equal to 0. So you solve those two equations separately, and you get very easily here x equals 0 or x equals minus 2. So it must be at these two x values, 0 and minus 2, that is where the tangent line is going to be horizontal. I wonder if I believe that. Well, I'm going to check it. So I actually have a graph of this original function made here. Okay, so let's look at the graph. I can find it. Oh, here it is. All right. So there's the function of x cubed plus 3x squared minus 1. And what did we say? The tangent line is going to be horizontal at minus 2. There it is. See, there's a turning point, right? So you have a horizontal tangent line, or the tangent line is going to be horizontal at x equals 0. And because that's what we found, right? There it is. You have a horizontal tangent line. Okay, right? By the way, over here on the left, the function is increasing. So over here, you know the derivative is, what's the sign of the derivative going to be? The sign of the derivative. See, here's the function is increasing. So what's the sign of the derivative going to be? Positive or negative? Someone answer me. Where the function is increasing, what's the sign of the derivative or the sign of the rate of change? What, Van? Say it louder, Van.
Positive.
Positive, right, Van? You're right. Yeah. So we know over here to the left of -2, the derivative is positive. Van, what about between -2 and 0? What's the sign of the derivative going to be?
Negative.
Negative. And what about over here on the right, past this turning point, what's the sign of the derivative going to be?
Positive again.
Positive again, yeah, because the function is increasing. Let's actually graph the derivative here. And let's, since we know what the formula is, let's graph the derivative. So y, I'm going to put it y equals instead of, whoops. No, why it always wants to capitalize this form here. So y equals, what was that derivative? 3x squared plus 6x, right? 3x squared plus 6x, right? Plus 6x. So there it is, okay? So the red curve is the, notice the red curve is the derivative, okay? So here's the original curve, that's the blue curve, and the red curve is the derivative. And see, notice where the red curve has x-intercepts, right there and right there. There are the x-intercepts of the derivative. What does that match on the original function? It matches the turning points, right? See, there's x-intercept of the derivative. It matches a turning point on the original blue graph. And Van, what you told me is where the original blue function is increasing, right? The derivative is positive. That's true, right? See, where this function, where this blue function is increasing, notice that right there, the derivative is above the x-axis. Where the blue function is decreasing, which is from here to here, notice the derivative is below the x-axis, so that means it's negative. And then back here, where the blue function is increasing again, notice the derivative is above the x-axis again. So that means it's positive. So, so your answers were correct, Van, and that's borne out by this picture, okay? It's always very interesting to graph a function and its derivative on the same set of axes, okay? All right. So much for that little demonstration there. That's the power of calculus now. We can, we know now a lot about graphs just from algebra without actually having to draw the graphs. That's going to be a tremendous time-saving device for us. All right, so let's look at the next example now. These are all examples of basic differentiation rules, right? So I want to calculate now f prime of x. So what's the rate of change function or the derivative function for 4x minus x to the 0.7 power? So again, you can go term by term here. You can start by finding the derivative of 4x, and then you move on to finding the derivative of x to the 0.7 power, right? Okay. All right, so let's start with the derivative of 4x. This again is a power of x. X by itself is x to the first power. So that is a power of x. So you can apply the power rule. So you can bring the 1 down. So you have 1 times 4, and then x to what power here? So what stays in the exponent now?
0.
0, exactly. Because you subtract 1 there, right? Minus now, this also is just a power of x, right? You have x raised to the 0.7 power. This power does not have to be a whole number, okay? It can be a fraction. So the power rule still applies. That's a really great thing about the power rule. That is due to Newton, okay? Newton is usually associated with the power rule. So bring down the 0.7, okay? And then you have x to the 0.7 minus 1. And now let's simplify this a little bit. So we have 1 times 4, obviously that's 4. What's x to the 0th power? Better known as? When you raise any quantity to the 0th power, what do you get?
1.
1. Okay, exactly. So we really have here a column 1 times 4 times 1, which obviously is just 4, right? 1 times 4, x to the 0th power is 1. So you really just have here 4. So you don't have to write down the 2 1s. Here we have minus 0.7 or 0.7, and then x to the minus 0.3. And I would just, I think I would just leave it like this, okay? So 4 minus 0.7 x to the minus 0.3. If you don't like having negative exponents, sometimes negative exponents are annoying to us. You can get rid of the negative exponent by taking the reciprocal, right? So this means the same as 4 minus 0.7 times x to the 1, 4 minus 0.7 times, and then x to the minus 0.3 is 1 over x to the positive 0.3. Remember, you can change signs of exponents by taking reciprocals. So this ends up as 4 minus 0.7 over x to the 0.3 power. Don't put the 0.7 in the denominator, okay? The 0.7 does not go down to the denominator because this exponent does not apply to the 0.7. This exponent only applies to x. If you wanted it to apply to the 0.7, you would have to put the 0.7 and the x in parentheses. So since they're not in parentheses, that the 0.7 is not affected by the minus 0.3 exponent. So you won't move it to the denominator if you're trying to change that exponent from negative to positive. All right, so see these basic differentiation rules, right? Really nice, very powerful. Let's try this one. This looks like a tough formula to find the derivative of, but it's really going to be a piece of cake. All right, so we have g of x is 2 over x plus 5 over x squared. All right, what I want to caution you about is don't start applying your derivative rules too quickly. Okay, so you may have to do a little bit of rewriting of the expression first before you use your derivative rules. So that's exactly what I'm going to do here. I'm going to write the 2 over x as 2 times x to the minus 1. See, x, of course, is x to the first power. If I want to get that x out of the denominator, and that's what I want to do here, I can pull it up out of the denominator, but I do that by changing the sign of the exponent. So 2 over x is the same as 2 times x to the minus 1 power. And I'm going to do the same thing right here. I'm going to bring that x squared out of the denominator, and I do that by changing the sign of this exponent. So 5 over x squared is the same as 5 times x to the minus 2 power. I need to do that because I need in this form before I apply the power rule. I cannot apply the power rule to these two fractions, right? These are not really powers of x until I write them in this format. Now you can find the derivative. See, I hadn't started finding the derivative yet. This is just rewriting the original function, g, okay? So now I can find g prime of x. That would be what? Bring the minus 1 down. So I have minus 1 times 2, that's minus 2, x to the, now what exponent do I have here?
Minus 2?
Minus 2, right. Subtract 1 from minus 1. Minus 1 is minus 2. Remember, you're always subtracting 1, but be careful about doing it with negative numbers, right? And then same thing here, bring the minus 2 down. So you have minus 2 times 5, and then x to the minus 2 minus 1 is minus 3. Now let's, that really is the formula for the derivative. So when you've got to this point, if this is the question on the test, you've got some partial credit already, because this really is the formula for the derivative. All that's left to do here is maybe simplify this a little bit, okay? So here's how I'm going to simplify it. The x to the minus 2, right? Remember, you can change that sign, the sign of that exponent back to plus by pulling that into the denominator. So minus 2x to the minus 2 is the same as minus 2 over x squared. Of course, here, minus 2 times 5 is minus 10. And again, I'm going to bring this x to the minus 3 back to the denominator to make that x to the positive 3. So minus 2 times 5 is still minus 10. That doesn't go into the denominator, but the x to the minus 3, I'm going to pull that into the denominator. The reason I went in this last step is notice my original formula did not have negative exponents in it. So I kind of want to make my answer correspond to the way the function was originally written. So since this a function was originally written not with negative exponents, but with these powers of x in the denominator, I'm going to rewrite my derivative answer so it looks like, in form, it looks like the original function. So that's kind of my rule of thumb. You want to simplify your derivative formula to kind of make it fit the same format as the original function. All right, let's see. I think I've got one more, and then I'm gonna let y'all try some. Okay, so before we break here, so let's look at this one. This one looks terrible. Okay, to find the derivative of. Probably if you graph this function, I don't have a graph of this one made, but if you graph this one, it's probably going to look, you're going to really crazy graph. Okay, this is called a rational function because you have a polynomial in the top of this fraction. This is a 5th degree polynomial because we have x to the 5th power here. And then in the bottom, we also have a polynomial function. This is a 2nd degree or quadratic function because we have x raised to the 2nd power. When you have a polynomial divided by a polynomial, that's called a rational function. And those are important types of functions, but they're very messy to graph. So, but we're going to learn something about the graph here without actually constructing the graph. All right, so but first, let's see if we can. What we're going to find out about the way we're going to be able to answer questions about the graph is by finding the derivative. So that's what I have to do first. All right, this doesn't fit into this because we have this x squared in the denominator. This does not fit into any of my basic differentiation rules. Okay, so if the x squared were missing. If the x squared were missing and we just had 4x to the 5th minus 3x cubed plus x squared, that would be pretty easy to differentiate. That would be easy to find the derivative of. But since I'm dividing by x squared, that really kind of negates all of my these basic differentiation rules that I know. But let me show you what we can do with this one. We can rewrite this formula a little bit to make it fit our basic differentiation rules. Here's what I'm going to do. I'm going to divide that x squared. Now, you may not know to do this unless someone told you this, okay? So that's why this example is kind of important, because I'm showing you here a little trick that may not be obvious, but it's useful. So you see what I did? I broke this big fraction. I wrote it really tiny here, so it may be hard to read what I wrote. But I took this this big fraction and I broke it up into 3 separate fractions. Of course, they all have to have the same denominator, x squared. So I broke this big fraction up as 4x to the 5th over x squared minus 3x cubed over x squared, and then plus x squared over x squared. So I'm allowed to do that because if I add, if you add fractions that all have the same denominator, you just keep the common denominator and add the numerators, right? Well, I just went in reverse here. I just broke this single fraction into 3 separate fractions, all of which have the same denominator, x squared. Now, the reason that turned out to be helpful, sometimes that's helpful, sometimes it's not. But in this case, the reason that turned out to be helpful is notice I can reduce each one of these smaller fractions now. 4x to the 5th over x squared, that reduces to 4x cubed because you can cancel some of the x's. You can reduce x to the 5th over x squared. That simplifies to x cubed. So you can divide out the x squared. And same thing's going to happen here. 3x cubed over x squared, you can divide out the x squared into the x cubed, and you just get left with minus 3x because some of the x's will cancel. And this third one is even easier. X squared over x squared, that just has to be 1 because there you're just dividing a number by itself, right? So this formula for h of x, I can really rewrite that as just 4x cubed minus 3x plus 1. And so now it's really easy to find the derivative when you have it rewritten like this, because these are powers of x now. So h prime of x would be, let's see, to find the derivative of 4x cubed, bring the 3 down. So we have 3 times 4x squared, subtract 1 from the 3. And then here, the derivative of minus 3x, remember this is x to the first power. So you get minus 1 times 3x to the 0th power. And then the derivative of that constant is 0. The derivative of 1 is 0. So you end up here with 12x squared minus 3. Wow, turns out to be really easy there. Remember, x to the 0th is 1. So this just disappears. You get minus 1 times 3, which is minus 3. So easy there. There's the derivative function. All right, let's use that derivative function now that we've got it. It took us a little bit of work to find that, right? So let's apply it a little bit here before we finish this question. So here's here's how we're going to apply it. I want to find the equation for the tangent line to this curve, whatever this curve ends up looking like. I want to find the equation for the tangent line to that curve at this point. Okay, so I claim that this curve that you get when you graph this big formula here, I claim it goes through this point. You can check that just by plugging minus 1 in for x here, and when you do that, you're going to see that you end up with an output value of 0. So this curve does go, whatever it looks like, it does go through this point. And I want to find the equation for the tangent line at that point. Wow, I'm not even going to draw that tangent line. So again, this is a very geometric question, right? A very graphical question about tangent lines to curves. That's a very graphical question, but I'm going to do this all with algebra. I'm not going to draw any graphs at all, okay? So I'm just going to do this all kind of in my imagination. What is the equation for the tangent line at this point, okay? All right, so let's think for a moment now. If you write down the equation for a line, a tangent line is just a line. So if you write down an equation for a line, what piece of information or pieces of information do you need to know to write down the equation for a line?
You need 2 points.
Yeah, well, it'd be nice if I had 2 points, okay, right, Colin? Okay, because what, Colin, will you do with the 2 points?
Use the that slope equation.
Slope, right. You need to calculate the slope. So that's one thing we need when we find the equation for a line, right? We need the slope. So, all right, so that's, I got to figure out what the slope is, right, for that tangent line, okay? So what is the slope? And once you know, and so one way you can do that is by finding 2 points and using the slope formula, correct? Okay. And then once you found the slope, Colin, then what do you do?
Then you need to find the y-intercept.
Yeah,
Is that
you
right?
can find the y-intercept, but you really don't have to find the y-intercept. Once you found the slope, you can jump right to the equation by using the point slope form. Okay, if you know the y-intercept, that's great. But if you don't know the y-intercept, you just need to know some point on the line. It doesn't have to be the y-intercept. Do you remember the point slope form, Colin? It looked like this. It was y equals m, which is the slope, of course, times x minus x1. That's x coordinate of a point on the line, plus the y coordinate of that point. And so you need to know a point on the line. But the point doesn't have to be the y-intercept. I mean, if it is the y-intercept, that's nice, but that makes everything easier. But it doesn't have to be the y-intercept. So we need to know a point on the line. But do we know a point on this line? This tangent line?
Well, you gave us one in the question.
I did, right? Okay. All right. Because this tangent line, right, is at this point. So this tangent line has to contain this point, right? Okay. You know, the curve is going to contain this point, but remember, the tangent line is going to touch the curve at this point, right? Okay. So so we know a point that's on the line. It's -1 and 0. Okay. Which isn't actually the that isn't actually the y-intercept for that line, Colin. That's actually the what intercept?
X?
Yeah, that's the x-intercept,
X-intercept.
right? Okay. So unfortunately, we don't know the y-intercept, but it's okay. We know the x-intercept, and any point will do. Okay. So so I have a point, so I can fill in here in this point slope form. I can fill in -1 for x sub 1 and 0 for y sub 1. Okay, but I still have to find the slope. All right. So again, you can find the slope if you know 2 points on the line, but I do not know 2 points on this line. I do not know what the tangent line looks like. I don't know if it's even, I don't know if it's going up or down even, because I don't even have a graph of this formula. Okay. So, you know, at this point, I kind of have no idea what the tangent line looks like, except that it goes through this point, right? But I have a backup method here, right? Okay. So I don't need another point to find the slope. How can I find the slope in this case?
With a derivative, and you...
Derivative, right. That's what the derivative tells you, right? Derivative tells you slopes of tangent lines, okay? Derivatives mean the same as slopes of tangent lines. I asked that question, by the way, on the test, for instance, in problem 6, the one that I had the corrections on. So I asked the question 3 different ways. And so some of y'all got the first answer correct, and then you didn't get the second 2 correct. So when you see that, you're going to be kicking yourself. Like on the test, 6F says, estimate the slope of the tangent line at, in this problem, it had to be x equal 95. That turned out to be around -5. Most people got -5. Some people got a little bit more, a little bit less, but it was close to -5. Okay. So they got that answer correct. And then the very next question was, what's the instantaneous rate of change at 95? Okay. And all you had to do was recopy your answer -5. Okay. Because slopes of tangent lines are instantaneous rates of change. And then the next question was, what's f prime of 95? That's the same answer again. It's -5. You don't have to calculate it again, because derivatives are instantaneous rates of change, which are slopes of tangent lines. So you can find the slope of this tangent line not in an exotic way at all. Just use your derivative function. So we know what the formula for the derivative function is. You want to evaluate it at this point, -1. So just calculate h prime of -1. That's all there is to it. Let's see, h prime of -1 here. That would be 12 times -1 squared minus 3. So -1 squared is 1. So you get 12 minus 3. It's a big slope. It's 9. Well, we really don't care. So that's a really steep line because you got a very high slope. But that's of no importance to us because we're not going to draw the tangent line or we're not going to graph the curve either. We're just going to fill these numbers into our point slope form. So the equation for the tangent line is 3 times x minus a -1, which is really x plus 1, and then plus 0. So we get y equals 3 times x plus 1. There's the, see, so simple, right? There's the equation for the tangent line. So, something that before we'd have to do by, making a graph of this function and trying to draw a tangent line there, and that would be so messy. And, trying to pick 2 points off of the tangent line and, and then estimate the slope, and we would come up with, maybe the right answer, or maybe we would be off. Different people would get different answers. It would just be very cumbersome. But now everybody's going to get exactly the same answer, and it's going to be exactly correct. Right? See, this is what calculus now has done for us. So now we know the equation for this tangent line is exactly y equals 3x plus 1. It's hard to describe what a breakthrough this was in mathematics, because people had been thinking about. So you may wonder, why were they so interested in this problem? Okay, and there are lots of practical reasons for that. People have been thinking about equations for tangent lines for many thousands of years, all the way since the ancient Greeks, by the time calculus was developed. So being able to write down equations for tangent lines exactly without having to go through a cumbersome process to discover them, that was a real major breakthrough. Okay. All right. So took a long time, though, to discover how to do that. All right, so all right, it's break time. So we're gonna take a break, and then I'm gonna have y'all do a practice here with these basic differentiation rules a little bit. Okay, when we come back. All right, so we'll come back about 12:35. All right, so that gives us 5 minutes there to cool off, and then I'm gonna let y'all practice a little bit with these basic differentiation rules before you get to your homework. Let me see if I can pause the recording here. All right, let's resume that. Okay, I resumed the recording. Sorry, I had the chats off, so I couldn't see. Some people were answering questions for me, and I couldn't see it. So I made a mistake here when I was just writing down the formula for this line. This tangent line. So we had calculated that the slope of the tangent line is 9, and then that goes in here in the point slope equation for the line. But for some reason, I wrote 3. I don't know. I was thinking of 3. So there's really supposed to be a 9 here instead of a 3. All right, because we calculated the slope right, but I just didn't transcribe it right into the formula. Okay, so let me repair that in the notes. All right, so let's look at a few examples now. Oh boy, I don't know if we'll get a chance to do all of these, because I want to mention something else. But let's look at a couple of them anyway. So I'm going to have y'all try these, and if you don't have to get through every maybe not through every step before we answer them, but just try to get as far as you can. All right, on these. Let's start with A. So there we have this function f of x equal 5 to the 10th power. F of x is 5 to the 10th power. So again, in all of these questions, I want to calculate what is f prime of x. All right. So I'm finding the derivative, or if we're using the old-fashioned notation, that would be dy over dx. But here, f prime of x. All right. So the function, there's the formula, 5 to the 10th power. Can you write down there the derivative? Just take a few seconds to try that. Should not take long.
Is it just 0?
Van, yeah, thanks for volunteering. That's just 0, right? Okay. So yeah, Van, you're correct. 5 to the 10th power. Just the derivative is just going to be 0. Did anybody get carried away here and try to bring the 10 down and then multiply and then subtract 1 from it? So did anybody write this is the answer? 10 times 5 to the 9th power. Why is this not the answer, Van? Why is it 0?
There's no x there.
There's no x here. That's right. Okay. There's no x. So that means this formula is just a what, Van? Begins with a C. That's just a number. What do we call just plain numbers?
Coordinate.
Not a coordinate, but a constant. Okay. So this is just a constant. This is just a number. And remember the constant rules, because there's no variable here like x. All right. So no variable. So that means this is constant. And remember, our rule for constants is very simple. The derivative of constant is 0. So I was trying to trick you here to make you think that you would use the power rule to find the derivative. But no, the power rule is not involved here, because this is not a power of x. This is just a number, and so its derivative is automatically going to be 0. Okay, so the easiest type of derivative, all that will be your favorite derivative. All right, let's look at this one now. Okay, so but I want to point out that, so we want to find the rate of change here, the derivative function, but this involves a radical. Okay, and so very important thing to remember. When you want to find rates of change of radicals, we can certainly do that. We're going to do it here. But before you do that, you're going to have to rewrite your radical how? So you have to change your radical into what?
Is that a fraction?
Yeah, a fractional column, a fractional what?
Exponent.
Exponent, exactly. So we want to change this cube root into a fractional exponent. So you got to keep that in mind. You're going to be doing that lots in the class, taking roots and changing them into fractional exponents and then changing them back sometimes. Actually, we're going to change this one back too, okay? So how does this look as a fractional exponent? Nothing happens to the 2, that's the same. But the cube root of x is the same as x to what power?
1/3.
Yeah, Don, it's 1/3. Yeah, cube root is 1/3 power. So, and this is what you want to do first before you start trying to find the rate of change. Take the cube root and write it as a power, because then you have a power of x, and now you can use the power rule to find the rate of change. All right, so y'all try that. So we're really finding the derivative of 2x to the 1/3 power. Okay, so what does that derivative look like? Try to at least get one step here. Okay, the simplifying might be a little bit tricky here, but let's try to at least get one step in the derivative. So you don't necessarily have to completely finish it to just get as far as you can. All right, let's take 5 more seconds. I'm not trying to rush you, but well, I am trying to rush you, but you don't have to get all the way finished. All right, so let's look at this one now and see how far we got. I'm going to call on someone. Let's see. Who shall we talk about this with? Kevin, are you there? Arbasto, Kevin?
I am sir, but I'm kind of lost with it.
Okay, well, that's fine. That's fine. All right. We're going to get you found here instead of lost. All right. So, Kevin, we're starting from right here. Okay, at this point, and I want to find the rate of change function. So once I've got the derivative function, same thing. So once I've got it to this point, now I'm in great shape because I have a power of x. So now I can apply the power rule. Kevin. So what does the power rule tell me then about the derivative? So what's that process there to find the derivative of a power?
Looking through my notes.
What do you do with the exponent?
Move it to the left, or
yeah, you bring it down, right? Okay, so bring it down. So that would give us as a coefficient. So we would have 1/3 times 2 times x, and then how do we change the power?
Yeah, that's where I'm lost.
Subtract 1. So you would have 1/3 then minus 1. Okay. So you're going to do this like 50,000 times in the class. So so just get ready for it now. Bring the power down and then subtract 1 from the exponent. So let's see, that gives us 1/3 times 2. That's easy, Kevin. That's 2/3. And then you have x to the, what's 1/3 minus 1, Kevin? So if you take 1/3 and subtract 1 from it, it's going to give you a negative number. But what negative? It's going to be a fraction. What negative fraction is that? What's 1/3 minus 1? One-third is
yeah, -1, -2/3.
Yeah, perfect. Right. Yeah, -2/3. Right. Okay. So you have 2/3 x to the minus 2/3. If you get to this point, that's pretty good. Okay, that really is the derivative function. The rest that you can do with this is just simplifying that. Okay, to sort of make it look like the way the original function was written. Kevin, notice the original function did not have fractional exponents in it. It had cube root in it. So ideally, I'd like to take that and convert it back to a root instead of writing it as a fractional exponent. But this really is a formula for the derivative. So you could use this formula in your calculator, for instance, if you wanted to evaluate the derivative. Let me show you how you can clean this up a little bit, though, to make it look like the original function. So first, that's a negative exponent. So you can make that exponent positive by pulling the minus 2/3 x to the minus 2/3 down to the denominator. So you would have 1 over x to the positive 2/3. Don't change the 2/3 in front though. Okay, so it's 2/3 and then 1 over x to the positive 2/3. All right, that's step 1. And now you can rewrite the x to the 2/3 power, because when you have a third power, that a thirds here, that means cube root. So you'll write cube root, can barely write that legibly there. That's cube root. And the 2 in the numerator, that stays as a exponent. That doesn't change. So you get the cube root of x squared. So I have 2/3 times 1 over the cube root of x squared. Let me see if I can write that a little bit neater. So I'm going to multiply the 2 times the 1. So that's 2. And then 3 times the cube root, that's cube root of x squared. I don't know if y'all can read that very well or not. That's a cube root though. Okay, so there is the sort of final perfect answer, 2 over 3 times the cube root of x squared. That's really the same as this. I just wrote it differently. Okay. So radicals, like cube roots or square roots, you want to convert them to fractional exponents first before you try to find the derivative. And then you may have to convert them back to radicals after you found the derivative. Okay. All right, let's try this one. So this one's a little bit easier. All right, so here my function is just, even though the coefficients are messy, that's not really important. Here my function is minus 0.00 x cubed, I'm sorry, minus 0.0063 x squared plus 0.58 x minus 1. So I want to find again the formula for the derivative. All right, so see if y'all can find that quickly. So fortunately, our coefficients are a little bit messy, but the powers are nice. Okay, you just have x squared and x to the first power. You don't have something ugly like x to the 1/3 power.
I have a quick question.
Yes, Colin.
How do you vocalize a root that's not 2 or 3? Like if you say 5, do you say the 5th root, the 10th root, root 10?
Yeah. Mm-hmm. So you can change this. You can change this index. So if you don't have an index, that's understood to be square root, right? Then you have cube roots, and then if that's a 4, it would be 4th root, 5th root.
Oh, okay.
Yeah, there's no, that I'm aware of, there's no, there probably is, just not aware of it. You might say a quartic root or a quintic root. That's probably the right word, but you would never say that. I never heard that actually.
I was just asking.
Maybe that was said in the 1600s. I don't think people say that.
Yeah. Yeah.
All right, so did y'all find the rate of change of this? Is really just a quadratic function because it's x squared. So that's really, if you graph that, you're just going to see a parabola, but we're not going to graph it. All right, so let's see if somebody wrote down the formula for that. Louis, did you, Ruiz, did you write down the formula for that one? Louis, are you there?
Yes.
Yeah. Can you tell me what you got or how far you got?
Well, I got 0.0121.
You got what? Say that again.
0.0121.
0.0121.
Yes.
So what'd you do? You brought this 2 down, right? In front?
No, I didn't. That's when I messed up. I brought in 1 instead of a 2.
Oh, okay.
I
So
have to multiply by 2.
yeah, you have to multiply this by 2. Bring the 2 down and multiply it by this.
Yes.
So what's 2 times minus point? So you're going to get a negative here, by the way. What's 2 times 0.0063? It's almost this.
Yeah, it's 0.0126.
Yeah, 0.0126, right? And then x to what power?
1.
1, right? Yeah. So we don't have to write the 1 there. What about for this term, Louis? What's the derivative there? So we did the first term. What about the second term?
That's going to be 1 times 0.58.
Right. So 1 times 0.58. That's 0.58. And then what about the x?
The x is to the power 0.
Which is
0. 1.
No, 1, right. So in other words, the x just disappears. So you just get 0.58.
Yes.
Wait, sorry,
So-
why does it disappear?
Because what you have here is, this is x to the first power, right? So you bring the 1 down. So you have 1 times 0.58, which is just 0.58, and then x to the 0th power. But x to the 0th power is 1. So you really don't even need to write that. So you
Okay.
just really get 0.58. So there's kind of a shortcut here that we didn't write as a rule, but you can sort of remember it easily. If you just have a number times x, just a number times x, x to the first power, number times x, the derivative is just going to be the number. The x is just going to go away. That's x to the first power, though, right? So the derivative of 0.58 times x is just going to be 0.58, but that will be true for any coefficient. So if it were the derivative of 10 times x, you'll just get 10. The derivative of -5 times x will just be -5, and so forth. So it's really easy to differentiate just x. What about the derivative of Lewis -1? What's that?
-0.
-0, which is 0, correct? So there you go. So you don't even have to write that down. So there is your rate of change, -0.012 x 126x plus 0.58. Now, Lewis, there's another question there. So you're unlucky. You got this one that has two parts to it. It says, this is like we asked before. Find the values of x where the tangent line is horizontal. So we did that process before, right? Find the values of x where the tangent line is horizontal. Remember, how did we do that before? Where the tangent line is horizontal means what?
0 to 1.
Well, wait, okay. Yeah, answer my question here before you, I think you're getting ahead of me. When the tangent line is horizontal, what is happening when the tangent line is horizontal?
X equals 0.
What is, what?
Or y equals 0. Or x equals 0.
No, but something does equal 0. What equals 0 where the tangent line is horizontal? What?
The formula, the derivative.
The derivative. Yeah, there you got it. All right. So to answer this question, you take your derivative and set it equal to 0. So you just have to solve this equation. Okay. Well, that's a very easy equation to solve. So we're not going to actually go through the solutions there. All right. May need a calculator to help you with this, but that's it. Take the derivative and set it to 0. Okay. And then you can answer this question. Okay. And by the way, again, Colin mentioned this earlier, right? Where the tangent line is horizontal, that is where the turning point is. So we would be finding the x values where the turning points are on this function. By the way, this is a quadratic function. So when you graph it, you're going to get a parabola. Remember what parabolas look like? How many turning points do parabolas have?
1.
1. And that turning point has a special name for parabolas. Remember what the name of the turning point for a parabola is? Remember that? Here's what parabolas look like. They either look like this or they look like this. And that turning point is that point right there at the top of or bottom of the parabola. And that point has a special name for parabolas. It's a turning point in general, but for parabolas, we have a special name for it.
Vertex.
Remember what's that called? What?
Vertex.
Vertex, right? So by setting the derivative to 0, you're finding the vertex of this parabola. Okay, a problem that you've done many times without calculus. Okay, so that's a problem we can solve without calculus, but we can solve it really easily with calculus. Okay, so in these problems now, just to speed things up, let's not actually find the derivative, but I just want to show you, before you find the derivative, here's how you would rewrite the function. Okay, so you can find the derivative using our basic differentiation rules, but before you apply one of our basic differentiation rules, you have to rewrite these formulas. So let me show you what you would do. Y'all can make some suggestions for me. So how could I rewrite this formula so that I could find its derivative using one of my basic differentiation rules? What's the problem with this formula, the way it's written? There's no problem with the formula. I mean, it's a perfectly good formula, but in terms of finding the derivative, what's wrong with this formula?
It's not simplified, so you can throw 4 into a fraction.
No, I don't want to throw 4 into a fraction, Donna, because it's easy to find the derivative of 4. What's the derivative of 4?
Oh, true. That's 0.
That's 0. So that one I probably want to leave alone. It's this one is the one that's an issue. And the issue is X is in the denominator. So in those basic differentiation rules that we have, you cannot have X in a denominator. So I got to get the X out of the denominator. So I can do that. How do I do that? So how do I get this X up? You can't just pull it up willy-nilly, but you can do something to move it up. So what do you do to move X's from numerators to denominators and vice versa? Is someone answering that on the chat? Yeah, Daniel, you said it has a fraction, change the fraction. How do I change the fraction there? How can I move that X up?
Isn't it 2x to the power of -1?
Ah, that's right. Yeah, I can see right now this is X to the first power in the denominator. I can pull that up by writing it as X to the -1. See, when you move X from the bottom to the top, denominator to numerator, you can do that by changing the sign of its exponent. Do not pull the 2 up though, okay? Just leave the 2 in the bottom. So you still have 1/2 here, X to the -1. Now it's very easy to apply our differentiation rules to find the derivative here, okay? What about in this one? We don't have to do anything with the 4x. What's the derivative of 4x? I just mentioned, if you have a constant times x, what's the derivative of that? It's very easy. What will the derivative of this term be?
Four. Oh,
4. Yeah, just going to be 4. Yeah, anytime you have a constant times x, the derivative is just the coefficient. Okay, so this one is easy to differentiate. This is the one that's hard to differentiate because first you have a square root. Okay, that's a problem. So we have to get rid of the square root, and even worse, the square root of x is in the denominator. So how can I how can I rewrite that square root? First, change that back to a fractional power. So square root means what power of x? Yeah, you said it there, Daniel. It's x to the 1/2 power. Perfect. Okay. So 3 over the square root of x is the same as 3 over x to the 1/2 power. But I still have x in denominator here. So I want to pull that up. How do I do that? We just did it here. What do you do? Yeah, change the sign of the exponent. So don't do anything with the 3. The 3 is going to stay, but now this becomes 3 times x to the -1/2 power. So pull x to the 1/2 power up. It's going to now go with the 3, but it becomes x to the -1/2. Now you can find the derivative function using our basic differentiation rules that we've been talking about. Okay. Let's look at one more here. Any suggestions on this one of what we can do? See, again, this x is a problem here. It's in the denominator. Let me show you what I would suggest. Break this up into 2 fractions. Break that up into 2 fractions. So you have 8x minus 1 over 2x. Break that up into 2 separate fractions with a denominator of 2x. Now, let me show you why that helps. Because here, this x divides out. So you just get 8 over 2, which is 4. That's nice because the derivative of 4 is 0. So that's really easy. Now, what do I do with minus 1 over 2x here? Well, just like we did in one of the early examples, don't care about the 2, but bring the x up. So you get minus 1/2, the 2 stays in the bottom, times x to the -1. And now you can find the derivative of the function when it's written like this. But when you have it originally written like this, it's going to be hard to find the derivative of. But now when it's written in this form, which looks ugly, but much easier to find the derivative in this form than in the original form. Okay, I want to add here before we run out of time. Whoops, I've got to add a couple of very simple differentiation rules for you. So to our list. And we're now going to involve some trig functions, okay? So we haven't been dealing much with trig functions in the course, but we're gonna start dealing with them a little bit more now, okay? And so here are two famous and easy to remember formulas. They're really miraculous, all right? Formulas, and they turn out so nice. So the sine function, okay, one of our, our very basic trigonometric functions, right? The sine function, that's a function, so it has a derivative function. But nicely, the derivative of the sine x, so this is really a stroke of luck, the derivative of the sine x, guess what? It just turns out to be cosine. That's almost a miracle, okay? Every time I think about that, I'm really amazed. The derivative of the sine x is just cosine x. So that will be one of your favorite derivative rules because it's so easy to remember. The derivative of the sine x is the cosine x. And the same is almost true for cosine, okay? So derivative of cosine x, as it turns out, is also sine x, except with one little catch, and this is what you have to recall. It's minus the sine of x. So derivative of cosine x is not just sine x, it's minus sine x. So derivative of sine x is cosine x, very easy to remember. Also easy to remember with this one extra catch, derivative of cosine x is minus sine of x. So that's very convenient. It's so great that the derivative of the sine x didn't turn out to be something really weird, okay? Because the sine x is kind of an unusual function, right? So when you think about its derivative, you might expect it to be something really exotic, but it doesn't turn out to be something exotic. It just turns out to be the cosine. And derivative of the cosine just turns out to be minus sine. Okay, let's practice that just a little bit in a few minutes. So I want to find the derivative of a couple of trig functions here. So suppose f of x is 5 sine of x, and we want to find f prime of x. So remember, here you have a constant. So the constant is not going to change your derivative at all. That will just stay in the derivative as 5. So only thing you really have to differentiate here is sine of x. And we just learned what's the derivative of sine of x?
Cosine x.
There you have it, cosine x. So it's just easy. The derivative of 5 sine of x is 5 cosine of x. Just that simple. So you see, you're going to like that one. That one's just so easy. Doesn't involve a lot of ugly algebra and so forth. Let's look at this one. The y is cosine of x over 2. So we want to find the derivative, dy dx, or you can also write that as y prime if you want to use the prime notation. Before you find the derivative here, I would suggest slightly rewriting this. You really don't have to, but I would write this as 1/2 times cosine of x. So cosine of x over 2 means the same as 1/2 times cosine of x. So when you take the derivative of this, again, you have this constant multiplied in, but that doesn't change the derivative of all at all. You just keep that constant. So you keep the constant 1/2, and then you just have to remember what's the derivative of cosine of x. And we just said it. Well, what's the derivative of cosine of x?
Negative sine x.
Yeah, so it's minus sine x. So you just fill in here a derivative of cosine of x is minus sine of x. Remember, you're multiplying here, not subtracting. So your final answer here is minus 1/2 sine of x. Or if you want to, you can write that as minus sine of x over 2. But really, this is the key step to get to. Your derivative is 1/2 times minus the sine of x. Let's look at this function, x plus sine of x. So there we're mixing function types a little bit. Here we have just x to the first power. X to the first power is a linear function, and then we're mixing that by adding it with this trigonometric function. So I'm mixing up an algebraic function here, this linear function with this trigonometric function to form a new function here. But now let's see what its derivative is. And again, you can go term by term since you're adding these two expressions together, right? So what's the derivative of x? Got to be really easy. What's the derivative of x?
One.
1, right. Okay. See, x is 1 times x. And remember we said, right, when you take the derivative of some coefficient times x, you just get the coefficient. So the derivative of 1 times x is just going to be plain old 1. And now it's so easy also, what's the derivative of sine of x, as we just learned?
Cosine x.
Yeah, cosine x, right. Okay, so there you have it. Your rate of change function is 1 plus cosine of x. Now let's answer that same question that we've been answering several times here. Find a value for x. So it's worded a little bit different here, but find a, not the, find a value for x where the tangent line is horizontal. So we've answered that question now several times. To find where the tangent line is horizontal, what do you do with the derivative? Louis, you just told me this a moment ago. To find where the tangent line is horizontal, what do you do with the derivative? You
Set it to 0.
set it to 0, right? So you just are going to set this to 0, and then you have to solve that equation. Oh, now we have a trigonometric equation to solve. God, nobody likes those, right? So let me see if we can figure this out, though. So we have, let's pull the 1 over to this side. So I have cosine of x is equal to minus 1, and then I just have to think about this. So I have to use my, use my powers of inspection here. What x values give you cosine minus 1? Let's think about some angles here. So if you have an angle of 0, so if you have a flat angle, I'm trying to draw an angle here, but I want it to be flat. What's the cosine of 0? Do y'all remember cosine of 0?
Is that 1?
It's
on a
1.
unit circle, right?
So yeah, Colin, it's 1. Cosine of 0 is 1. So 0 is not the answer to this, is not the solution to this equation, right? Because cosine of 0 is 1, not negative 1. Okay, so that's not quite it. If I open my angle up to 90 degrees, pi over 2, if I open the angle up to pi over 2, that's 90 degrees in degrees, right? Then what's the cosine? So what's the cosine of pi over 2? Cosine of 0 is 1. What's the cosine of pi over 2? You remember?
0.
Cosine of it's 0. Yeah. So cosine of pi over 2 is 0. So that's not the answer here either. X is not pi over 2 because cosine of pi over 2 is 0. Darn it. Now, if you open the angle all the way up to pi, so if you have an angle of pi, which is 180 degrees, so that's an open angle, what is the cosine of pi? You remember what the cosine of 180 degrees is? What, Dan?
-1.
That's -1. So there is one there's lots of other solutions to this equation, but there's one possible solution to this equation. X is pi, okay? Because cosine of pi is -1. So at x equals pi, if you graph this function, at x equals pi. So pi on the x-axis about 3.14, right? On the x-axis, you're going to get a horizontal tangent line, okay? So you're going to have either a peak or a valley on this curve at x equals pi. Okay, we're out of time. Okay, well, this next example is pretty straightforward, so I think you can do that one. All right, so let's stop there. Okay, so well, it's time for spring break, right? So be working on your homeworks, right? Especially that basic differentiation one that's due immediately after spring break. We didn't get to talk about the product or quotient rule, so we'll have to save that for after that homework for after spring break. Okay. So I will see y'all in a week. Have fun.
All right.
Thank you so much, Professor. Have a nice spring break, everybody.
Thank you.
Bye.
Bye. Have a good break.
Thank
Bye.
you. Oh man, you know what I should have said? I should have told them we'd be holding sessions over spring break.
You are holding sessions over spring break?
Yes,
Oh,
sir.
well, you can email them.
Yeah, I'll probably just send an announcement like, "Hey guys, forgot to say, but I'm holding sessions over spring break."
Okay, yeah. So Madison, two things there. You can
Mhm.
do are go over the test if people have test questions, and
Yeah.
then talk about this homework, basic differentiation.
Mhm. Yeah, I guess